All right, welcome everybody to my talks. I want to talk a little bit about my and our adventures with zero knowledge proofs and how we have been working on minting NFTs. Just a little bit about myself. I'm one of the co-founders of Centrifuge. Centrifuge is a Berlin-based project, and our sort of problem that we're solving is we're working on allowing companies to access to credit on Ethereum. So we come from this space. We love supply chain finance. Just a little bit about how big this space is. There's around $180 trillion transacted between businesses. And at any given point in time, around $30 trillion is locked up in outstanding payments. So that means there are invoices that are waiting to be paid where there's a legal contract that already says it must be paid, but the buyer is just saying, I need 60 days to pay this. The factoring sort of industry tries to solve this. Is probably the oldest solution to this problem where companies want to access this cash beforehand. We have the supply chain finance case where you start working with the buyer together to, for example, use their cash or cash from an investor to advance these payments. And this is sort of what we've been doing at Thalia. But really what we want to get to and where we see the advantages of bringing this into an open and decentralized world is, well, if you look at the access to this capital, what it looks like today is that a Global 2000 company is borrowing on LIBOR plus 50 basis points, so somewhere around 2.7%. This is an actual number of a big corporate that is getting money from a bank to pay their invoices or get paid early on invoices. But if you're a small pizza joint or a small business that doesn't have the negotiating power of a big corporate, your interest rate is a multiple. And we can address this by giving these smaller companies leverage by allowing them to have verifiable data that they can use to show who their buyers are, what their transaction history is, and sort of reduce this cost of underwriting these assets. And so why am I talking about this at a zero knowledge proof workshop or event? I want to talk a little bit about why or where we're looking at the potential for SNARKs, what our journey was with that, and coming from a very practical standpoint. I'm going to talk about a use case, and then just a little bit of where I see the challenges and I see this evolving. So maybe a bit of a disclosure, unlike most people in the room here, I actually don't even have a computer science degree. I dropped out when I was 19, started a software startup, and said probably setting up databases, gluing a few web frameworks together, and building a web product is all that I'll never do in my engineering career. And so I decided actually to drop out and do this stuff that sounded much more fun. Little did I know back then that I would be looking into all of this math and this stuff a few years later. But my perspective is looking at how do we get privacy into Ethereum? How do we get the other 99% of people that are not in this room, that are working with these technologies, that are building products today that don't have privacy, that are doing this in a way that's going to be at a disadvantage for smaller players, where there's going to be an issue with privacy. They're going to have all of these issues that we're all very aware of. How do we build stuff that gets them to actually do something? So February 2017, Vitalik probably brought zero knowledge to a lot of people in Ethereum that didn't know much about it, and wrote a few good explainers. There are opcodes in Ethereum to do zero knowledge proof verification for the old BN curve, but really no one was really doing anything on mainnet at that point. I personally first started playing around with it in November 2017. I was using Socrates, which at the time I think was already providing the easiest usability. I tried this very simple example. I want to create a zero knowledge proof, right, that I can prove I know two numbers such that a plus b is less than 15. It's actually as easy as pie to get this done. It took me some time to set up the Docker image and all that, create my prover, create my verifier, verify that transaction on Ethereum. But then this is not really that useful. So second example I tried to do is, you want to probably do something with a hash function, because that means you can commit to values on chain, but you can do some sort of logic in a SNARK off-chain? Well, 2017, doing it with Socrates was not an option. I could have started learning about wire boards and circuits and learning C++ or adjusting or refreshing my C++. I could have gone into libsnark, didn't want to do that, and said, well, clearly all of the Solidity developers that are going to be using this in the future, they're not going to do that either. This space is really not a place where we can see the dApp developers building stuff on top. So June 2018, still trying to get SHA-256 into Socrates. Thibaut Schäfer of Socrates was actually presenting at ZCon 0 in Montreal about, well, they've just integrated the libsnark gadget and they've got the most optimal implementation of SHA-256 in Socrates down from 270,000 constraints, which was quite ridiculous, to 27,000 constraints. So almost usable.
But even back then, the Sprout implementation had like around 30,000 constraints.
No, it always had 27,000.
Like, yeah, not 270,000.
No, so exactly. So going back, right, someone in between November 2017 and June 2018 implemented SHA-256 in Socrates without pulling in an external gadget, and that was very inefficient just because of the language features that were missing in Socrates.
Was that the libsnark gadget?
So the libsnark gadget then is, the libsnark gadget is the 27,000 constraints. So we brought it down to comparable to Zcash. There's still some edge cases where it wasn't as efficient, but that's negligible. But what also happened in June 2018, at least from my perspective, this was an ongoing development, of course, but, well, a whole bunch of new primitives came up that were starting being introduced by Zcash and then tried to be quickly adopted by others. Pedersen hashes, embedded curves, EDDSA, and this suddenly made the benchmark for, okay, what is acceptable zero-knowledge proof performance. It reduced this, I would say, by a factor of 10, right? Because usually the most expensive parts of a SNARK were those hash functions, the digital signature schemes, et cetera, et cetera. So Zcash sapling, proving a transaction or proving a SNARK was, I think, brought it down to 4 seconds instead of 45 seconds.
Still quite proud of this.
It is amazing, yes. And this is mostly thanks to Dara, and if you want to read about this, I really would say go to GitHub and look at the Zcash issues. They're probably some of the most interesting discussions and behind the scenes information on exactly how this all came together. So set the bar for, okay, now actually we don't want to use SHA-256 to create our Merkle trees because that's quite backwards. Pedersen is a few hundred constraints, whereas SHA-256 is 26,000, right? So fast forward 1 year, and actually, so this summer, Socrates implemented a standard crypto library over Baby Jub, which is the embedded curve in the alt-BN curve that Ethereum has, so similar to what the sapling Jub curve does in Zcash's BLS curve. So with that, actually, we are able to build SNARKs and use those tools that we want to build something. Which brings me to the second part. Remember I talked about supply chain finance, financing assets, getting NFTs into Ethereum. And so I want to show what we were working on together with a bit of help from the Socrates team to actually deploy this on a Kovan testnet. So for that, a little bit of background on Centrifuge. So Centrifuge is we started out as a peer-to-peer protocol. The main reason for that was saying, well, until we have fully homomorphic smart contracts, we cannot just put all of our data into a smart contract and have an invoice exist as a smart contract somewhere on Ethereum because of the obvious privacy reasons. But what we do need is we need Ethereum for certain things. So we have two main components on Ethereum. It's the identity contract, so a way for you as an organization to manage a set of public keys because, well, as a company, you can lose your private key and you want to replace that, or you just want to be prudent about it and change it, have different ones. So if this identity contract acts as a registry of your public keys they're using to sign messages off chain, and it acts as a way for other members in the peer-to-peer network to discover a node that you're running. The other thing we use it for is by relying on off-chain data. Mostly we lack this the work that the blockchain does. So we don't have a network of validators that validate our transaction. So what we still need to commit to them at least and get a timestamp and get sort of an agreed upon state. So what we do is when a message gets passed between different parties, we don't have global state, but at least we allow them to commit to these states on chain. I talked about this off-chain data that we anchor. And when I talk about off-chain data, this is, for example, an invoice, purchase order, a real estate property title, and so on. And what we commit to on-chain is a hash. But it's not just a hash of this blob of data. We actually take this and break it down into a key value store. We create a Merkle tree out of it, where each individual leaf is actually an attribute in the tree. Where each individual attribute is a leaf in the tree, such that you can create Merkle proofs of a subset of fields to sort of reveal selectively information. And this is, right now, we mostly do this on chain in public when we mint non-fungible tokens that sort of represent this, a claim, an aspect of an item. But the idea and the goal is for people to use those in snarks to use this data as a source of data for computation. So tying this all together, the way it works is Tire LLC sends an invoice to Bitcar Inc. This gets signed by both parties. The public keys of these are stored on chain. The transaction gets committed to on chain. So this is an invoice. It might contain line items. It contains private tax information. Contains all these things. We calculate this Merkle tree and we commit to that on chain. Now, as a supplier, what I want to do is I want to go to a bank and get my invoice financed. The way we see this happen is that I mint an NFT. I've used this abbreviation not because I'm used to talking to people in the background of Ethereum, but quick explanation. NFT, non-fungible token, it's a standard within Ethereum that basically is used to track ownership of anything. You basically have a serial number and an owner, and the owner can transfer that serial number to someone else. So unlike ERC20s that are fungible tokens where you have an amount and you can transfer different amounts, an NFT is not divisible and you can transfer it at once, only completely. So what we do is we have this invoice that exists off-chain, and so I want to now transfer this future revenue that this invoice represents. So the $10,000 that I'm getting paid 30 days later, I want to take that and say, okay, whoever owns this NFT is entitled to this money. So I can go to a bank or a bank in the cryptocurrency world and say, okay, if I give this NFT as collateral, I give this NFT to indicate that that the revenue that is associated with that invoice is actually should end up in your account. And so by selling that NFT, I can get financed. So roughly the structure is we have off-chain data about this invoice, exchanged between buyers and suppliers. We have an NFT that I can now mint from that information by providing these Merkle proofs about just a subset of information that I actually want to have publicly disclosed on chain. And then we have sort of products that allow you to take these NFTs and get them into something like a maker to draw a die from. But still not talking about zero-knowledge proofs until now. Well, we have this issue that these NFTs have some metadata that we need to have on chain to be able to price them, to create a marketplace for them. But we really don't want, as a supplier, really don't want to say who my buyer is, who's a debtor on this asset, what the actual invoice amount is. I might just want to borrow 50% of the invoice and not reveal that I'm actually making 100%. So we can do this by, instead of verifying these Merkle proofs on chain, we verify them within a zero-knowledge proof and just have these two elements as public outputs. And so this is essentially what we did with Socrates. We have a document data tree, which is this Merkle tree about the off-chain data. We have a third party that sort of acts as a rating agency or some sort of trusted party by the marketplace or by your counterparty that says, I accept these buyers and they have a rating of 0 to 100. And this rating agency publishes a Merkle tree of public keys and the rating. And so within the SNARK, what we do is we verify that the buyer signed this transaction. We match that with a public key that is present in this buyer rating tree and have as an output in the SNARK the rating that is associated a rating that is stored in the leaf along with the public key. So I talked a lot about our now 2-year journey to actually seeing how we can sort of drive adoption of this technology, how we can get users, dApp developers to build on top of the peer-to-peer network and sort of tokenize these assets. And I'm quite happy to say that with Socrates, this is quite possible. This is pretty much the core of the SNARK. It's about 80 lines. It does a few Merkle-proof validations. Merkle-proof verifications. It has these public inputs, public outputs. And in the end, it's integrated, and you can look at on GitHub sort of the code base that now mints an NFT based out of it. This is about 2.5 minutes of proving time, and I already know now we can probably cut that in half by doing a few simple tweaks. Now it costs 900,000 gas, and our like full on-chain computation verification of these proofs is around 800,000. So by the time Istanbul, the next hard fork in Ethereum, is going to be deployed, it's going to be significantly cheaper actually than what it would cost doing that without a zero-knowledge proof. And so we're doing that using the Socrates Pi crypto library, which has implementations of Pedersen and EDDSA for Baby Jub that allowed us to sort of use these cryptographic primitives that gave us this 2-minute performance for the proving time. So talking a little bit about what we did, I want to talk about the struggles we've had and the outlooks, and I apologize if this comes off a bit as a rant. It should be by no means, looking at where this entire industry was and where it's going. I think we're on a great path, and seeing an event here and people coming together, brainstorming about that, it's very encouraging. But like one thing that we see, Socrates and Baby Jub, and this is a very Ethereum-centric view, is not really really where we want to get to, right? There's discussion yesterday about why we shouldn't use alt-BN, but well, sadly, it's the only thing we have. Baby Jub has issues. I'd much rather build this for a different curve. Hopefully, Socrates and other technologies that are coming out of this are going to make it easy to migrate. Nevertheless, right now, this is a bit of a concern for us to invest significantly in any of this technology. About those primitives, right? I said, well, thankfully, Socrates has a Python implementation, but we don't use Python, and the Python implementation is slow, and sadly, we also don't use Rust, and even if we were, Zcash's implementation was not compatible because it's in a different curve anyway. So unless you are comfortable rolling your own crypto, you will end up not being able to use that hash function, or you have to implement it yourself, which is not ideal if you think of an application developer and not a crypto-focused company, right? I mean, just, yeah, finding the perfect hash function, it's probably a full-time job at this point. Looking at this space, this is changing so much. There's a few of them I tried to keep track. This is from my notes that I've been trying to maintain. It's like, okay, like what can we use that works in Ethereum? What can we use that also works in the zero-knowledge proof we want to use? Which one is secure? Trying to talk to people about that, and just like hopefully we get to a point where there are going to be a few choices, not as many as in here, and where there hopefully will be choices that will be workable for both Ethereum and other chains, as well as actually within a SNARK, right? Like it's great that we have Blake 2 in Ethereum. soon as a precompile brings down the gas cost a lot. Right now it's prohibitive. But if you look at the number of constraints, that's still not nearly close to Pedersen or MIMC. So that's one of the things that really needs to get better. It's just these hash functions. The other thing are signature schemes, right? Standards like how you do how you implement EDDSA is probably a million ways. Of course, this depends on the curve, but having some sort of libraries that we can use. We need to support hardware security modules. HD key derivation would be extremely helpful to actually get people to use this stuff. So those are the areas that I'm looking forward to seeing innovation and standardization coming together. And then the last point, I think, and I'm very happy that this is maybe not as big of an elephant in the room anymore as it was for the last few years. I'd say the number of companies that could reliably pull off an MPC that was secure and trusted, and then go through all of this work to convince the community that it is secure and trusted, is quite low. And if I think of our users who just want to create NFTs and want to tokenize their invoices, houses, or who knows what, like we can't expect them to set up an MPC, right? So I'm very excited to see what the next proving scheme will be that will come out of this. But yeah, maybe someone else has another favorite. No, but yeah, knowing full well though, again, that I mean, this is the cryptography we use here is in any other category, this would be considered I don't know, like basically we're doing human testing on highly experimental medication or whatever. So I have to be a little bit careful and not get too overzealous. We need to have something where we also need to make sure it's secure, and the people in this room can do that, but for industry adoption, those people can't. And so again, standardization on that and having good materials on that will make this dream of privacy and privacy preserving tech as a default for all of these dApps on Ethereum and so on as a thing. So thanks a lot, everyone. I hope I've been able to share a little bit of what it looks like from the other side, and encourage everyone to keep working on this stuff.